This is part one of the rivets and bolts subsection of the structural design section of our aero engineering course. A rivet is a permanent mechanical fastener. It's a smooth cylindrical shaft that may be solid or hollow. See, here's one I drew for you. That's the shaft that goes through the holes of the material you want to rivet. This rivet is placed through drilled holes in two or more sheets of metal, like a wing skin and a wing rib. For instance, a rivet tool pulls the shaft so that the ball on the opposite end, see there's a little ball on the end, or you might want to call it a wedge. It forces this rivet, starting right there, all the way to where it meets the metal sheets that you're riveting together. It forces this rivet to expand against the metal sheets. This squeezes the metal sheets together tightly. When they can be squeezed no more, the shaft breaks away from the ball. It's right there. You can't really see it in this rivet. Here's a real rivet. You can't see it here either, but between that little ball right there and this shaft here, they're connected with a diameter that's slightly smaller than the rest of this, so it's going to break off right there. It's going to leave this inside of here. This will look like a little wave moving along here as it squeezes against the metal. Look kind of like a snake that just swallowed a frog until it finally gets so tight that it can't squeeze anymore, and then it'll break off, and this part will be discarded, and this part will be left holding two pieces of metal together. Here's a rivet tool. So we stick it in there and squeeze like that. Well, it's not squeezing too good. As you can see, these rivet tools aren't known for their longevity. They get where they don't want to take a bite anymore, but a good rivet tool would pull that thing inside of there, and that would get bigger and bigger, and you'd have two metal sheets riveted together as a result. Okay, the shaft is then removed from the rivet tool and discarded, and the rivet's left in place, tightly holding two or more sheets together. Okay, here's a solid rivet. Okay, it's placed in a drilled hole, and since there's no shaft in the middle to pull it out and make it bigger, it's just compressed on the other end, either squeezed or hammered. Anyway, the other end ends up looking like this, where it's way bigger than the original hole, so it can't come out anymore, and you've got these two sheets riveted together. Okay, if you don't want your two or more sheets or plates of metal permanently pinned together, a bolt and nut can be used. Okay, this is used for attaching wings to fuselages, for attaching struts to wings. A nail going through two or more boards can be thought of as a rivet. The strength of such a joint is calculated using the same mathematical concepts. There are several ways that a riveted joint can fail. Here's a single shear joint. You can just pretend this is a 1-inch board and this is another 1-inch board and this is a nail between them. Well, this isn't really going to happen in most cases, but this picture shows that the nail is being sheared. Most nails are way stronger than that, and they're going to bend and compress the wood instead of shearing, but this is one of the ways that a riveted joint can shear. That's how boat propellers are set up. They have a little brass pin going through there. Whenever your propeller hits a stump or sandbar, instead of breaking the propeller shaft, it'll just shear your shear pin. Okay, here's a double shear joint. Okay, this is another way a riveted joint can fail. The rivet can bend. The riveted material can be crushed. See this little dotted line? This is where the bottom of the original hole in these side boards. Let's say these are 1/2-inch boards here, and this is a 1-inch board. Well, looks like the 1-inch board's pulling the nail better than the 1/2-inch boards are holding it down. You got dotted line drawn below where the rivet is there, and a dotted line drawn below where it is there. So it's crushing the material at the top of these 1/2-inch boards. See there, crushed material. And here's a single shear riveted joint with crushed material. These dotted lines represent the original hole, and obviously this board's being pulled up, this board's being pulled down, which makes the nail swing that way, which means this part down here is crushed riveted material. This part up here on the left board, but the right side of this left board, is being crushed by the nail there. And you have a little bit of material being crushed here on the ends too, because this nail, it turns and you have a net force on the end, a net force here, and a force shearing between. We'll get to that later. A riveted component could break. Here's one that just broke across there because that was too weak. The bearing surface area that's used to calculate the strength of a riveted joint is the rivet length multiplied by the rivet diameter. Here's a rivet. Okay, we can say this is the same rivet. So the length there times the diameter, those are the units that we use to determine the bearing surface area. You might ask, why the rivet diameter? Why not the rivet circumference? See, the circumference goes all the way from one side to the other, or half the circumference anyway. Circumference is all the way around. But if this rivet here is pressing against all this material, why don't we count all of it from here all the way over to here? Well, the reason is because this rivet, well, down here, it's pressing straight against this riveted material. But over here on the side, its resultant vector is pushing off to the side. So the downward component on it is not equal to all this length, half of the circumference, but only to the diameter. Okay, yeah, here's a little bigger drawing of, let's call it the same rivet. And as you can see down here, where it's pressing straight at the material, you get the whole goodie out of the push. But over here, up closer to the sides, the rivet is pushing in that direction. So we only count from here to here, the rivet diameter times the rivet length as the surface area for calculations of how strong a riveted joint is. See, like this little part here, we draw it a little bigger here, and we have this part versus this part. We can imagine it's pushing on the side that much, it's pushing on the bottom about that much. This curve area is pressing mostly sideways. It can be thought of as pressing downward on this area and sideward on this area. Of course, a riveted piece of material must have enough material on the press side, you know, the bottom side. If we're talking about the same rivet on the last page where it breaks along here and the rivet's pushing against down here, we call this the pressed side. Well, obviously this is pretty thin right here, and this rivet's going to push sideways on this material and try to spread that apart, try to break that. Okay, sometimes a dimpling die is used to make two thin sheets of metal bowl shaped. See, there's a drawing I did. Those little lines there represent the top of the bowl, and there's a hole drilled through the bottom of it. This is how it would look if you were to cut it right across here and turn it and look straight at it. See, there'd be the hole right there, like that hole, and that part up there where it bends down like a bowl up there, that would be that part. So you get two sheets of metal like that, and you rivet them together. And it's a little stronger joint than if you just had two flat sheets. It's like when you're trying to take two plastic bowls apart. You have to lift one out. You can't just pull it sideways. Okay, this enables the top of the bowl, which contains more bearing surface area, to contribute to the strength of the joint. Okay, it also enables a flush riveted surface. See here, this top here, the top of our little triangular shaped rivet is flush with the top of the wing skin. And if that's what you're using it for, and that cuts down on the air drag. A single shear riveted joint is about 1/4 as strong as a double shear joint. Well, that's if they fail as a result of crushed riveted material. If they fail as a result of the rivet being sheared, then it would be half as strong. See, because you have one spot where the rivet's trying to shear on this single shear joint, you have two spots where it's trying to shear on this double shear joint. So if the weakest part of this joint is the rivet being sheared, like for instance a brass pin in a boat propeller, well then this would be twice as strong as this. But if the joint fails because of crushed riveted material, then this is going to be 4 times as strong as this. Even though the bearing surface areas of these two joints are equal, let's just imagine this being a 1-inch board, this another 1-inch board, this a 1-inch board, and these, that's a 1/2 inch and a 1/2 inch board. You still have 2 whole inches across there, as in here. You'd have 1 inch pulling down in each case, 1 inch pulling up in each case. So they'd be similar joints, but one's a double shear, one's a single shear. Okay, even though the bearing surface areas of these two joints are equal, the joint on the right is much stronger. The joint on the right will withstand twice the load of the joint on the left if the joints fail because of rivet shear. The joint on the right will withstand 4 times the load of the joint on the left if the joints fail because of the riveted material is crushed. Let's say we have a nail going through 2 boards. Here we go, there's the head of the nail. Just is long enough to stick out a little bit past the second board. Call these 1-inch boards. Call it a 2 1/4 inch nail or so. Okay, when the left board is pulled up, okay, we're holding this board up, and the right board is pulled down, well then this nail is going to do like that, ever so slightly. You might not see how much it does that, but it does do it a little bit. Kind of like when a gnat slows down a freight train. You can't, it's hard to measure, but you know it has to happen because of the laws of physics. Okay, the nail goes up and the point of the nail goes down. Okay, the head of the nail up, point down. Okay, let's say these are 1-inch boards. Let's say that in the left board, the distance between the nail head and the pivot point, see there's a nail head, this is a pivot point here. If you're going to pull down on this nail, let's say you just cut this nail in 2 and threw that board away, but you tied a rope to this nail and you pulled it down. Well, you're pulling down on the nail, so something has to push up on the nail. This wood's pushing up, but what's keeping the nail there? Why doesn't the nail just flip out? Well, the reason it's staying there is because you have a force over here pushing the nail down. You have more pushing up from there to there, more wood pushing up on the nail than you have wood pushing down on the nail from there to there. But if you're going to pull this nail down on this end, the force that you're applying to it here plus the force that the wood is pushing on the nail here equals the force that the wood is pushing up on the nail here. It's like a teeter-totter. It has to balance. Okay, so we're going to call this Y, and let's call this 1 minus Y. Let's say F1 is the force that we're pulling up on our left board. F2 is the force that we're pulling down on our right board, which is going to be the same as that if we assume this is all weightless. Okay, so we'll call F3 the force of the wood pushing down on the nail to the left of this pivot point. There's no stress at the pivot point because the nail is at the same place relative to the wood. Here the nail is up a little higher than it was before. Here the nail is a good bit lower than it was before. It's more lower here than it is higher here. And the same goes for this other board.